let's take a look at some of the basic things that we might do with matrices. So again, matrices, or a matrix, is just a grid of numbers. And I usually think of them as having m rows and n columns. Remember, it's always rows before columns. So anytime you're talking about something like the sub-indices on an element in the matrix, if you say something like, what is the element A42? That means you go down to the fourth row and over to the second column. Right? We're always doing row by column, and I tend to use the labels M and N. That's totally arbitrary, but this is, well, it's arbitrary, but it's tradition that is widespread enough that if you mix it up, you're really going to confuse people. Everyone does it this way. Always row and then column. So let's say we've got a couple of matrices. So let's just say there's 1, 2, 3, 4, 5, 6, 7, 8. Actually, you know what I'm going to do? You know what I'm going to do? I'm going to make this a 4. I'm going to make this 6 over 2. Hey, that's 3. That way I don't have to rewrite too much. It's easy to make a 5 into a 4. 4, 3, 2, 1. So what happens when I add these two matrices together? Well, I've got 8 numbers. There are a number of ways that we could potentially put these numbers together, but ultimately the rules say we just go element by element. So 1 plus 4, 2 plus 3, 3 plus 2, 4 plus 1, we get 5, 5, 5, 5. Right? So we just go here to here, add those together, and that goes here. Here to here, add them together, and that goes there. Easy peasy. Now, that worked with two 2x2 matrices, but that raises this other element of this, which is we have to think about our dimensions. So when we're adding, and I'm sure you can imagine, subtracting is going to be just as easy, right? So 1 minus 4, that would be what? Minus 3. 2 minus 3, that'd be minus 1. Actually, we can do that. Let's give these names really quick. So we'll say A and B, and we can ask, what is A minus B? It just stuck in my brain. Now I've got to do it. Minus 3. 2 minus 3 is minus 1. 3 minus 2 is 1. And 4 minus 1 is 3. All right, cool. So subtracting, just as easy as adding, as long as they've got the same dimensions. Same number of rows. Rows always come first. Same number of columns. So we can't subtract this taller matrix from this shorter matrix. It's just not going to work. Now, I will, very brief digression, we'll talk about sort of a version of this in a second when we talk about multiplying. But we could think about maybe a simpler problem where there might be a kind of an obvious way to do it. So let's say we've got some matrix like this. We'll say it is m rows and n columns. And we want to subtract something that is 1 row by n columns. In a situation like this, this is something that you might see while working with data, right? So this could be, say, a part of a normalizing process where you take some data and you subtract the average for each observation, something like that. So in a case like this, it would be sort of natural to think about, we call this broadcasting, basically just repeating this. So that's something you might bear in mind because, like I said before, realistically, you're doing this stuff on computers. Now, you might also go off and get a PhD, in which case you're going to be doing the paper and pencil matrix algebra. But for this class, it's good enough to just say, if we're adding and subtracting them, they've got the same dimension. If we have different dimensions, we're just saying we're not adding and subtracting them. Although we might just remember, in a case like this, these are sort of conformable, right? This we can just repeat neatly over this, which you might have to do in practice, but we're not going to worry about it. So dimensions, again, I'm going to repeat this just because this is probably the most important thing. It's rows and then it's columns. It's a little thing, but it'll keep you grounded to be following the same basic rules. The way that I think about this, so we're going to build up to matrix multiplying, but I sort of will use my hands to visualize a matrix multiplication. And in a case like that, we're basically going to be sort of adding and multiplying rows and numbers here. We'll see it in a second. But having this sort of notion of a length here and a corresponding length here, and maybe the widths are different. For me, just focusing on the dimensions and sort of imagining these rectangles that we're going to kind of smush together in a clever sort of a way, that's really going to be the key to sort of getting a sense for working with matrices. All right, so how can we multiply them? Well, the easiest case is just scalar multiplication. And to think about that, just think about you scale it up or you scale it down. So what is, let's say, 2 times a? Well, we just multiply each element. So 2 times a, we would get 2, 4, 6, 8, right? Just multiply by each element. Nice and easy. Vector multiplication, we come into this issue of dimensions. So I'm actually going to take a skip here and go into matrix multiplication first, because this is just what fits into my brain best. So if we've got an m by n matrix, and this is an n by o matrix, so okay, O will be fine. We can use O. These are matrices that we can multiply, and the result we're going to get out is going to be the outer dimension. It's going to be m by O. So we're going to get something that is as tall as this and as wide as this. And exactly how we'll do that in a separate video just to break it down really explicitly. But if we are doing vector multiplication, we are doing the same thing, although, of course, again, we might think about a setting on a computer where you want to multiply everything in a row by the same amount, or everything in a column by the same amount. So we can use that broadcasting on the computer if we want. But on the pen and paper matrix algebra, right, linear algebra properly understood, not just dealing with matrices and vectors in data, the math of it, not necessarily how we specifically manage numbers. But the math of it, we're going to have the same basic thing, but now we're going to have a 1 by n to match up with an n by something. I'm going to call this n by m because I don't like using O for that dimension, right? Or if we have, let's say, an n by m matrix, we could multiply that by an m by 1 matrix, right? And in this case, we're going to get back something that's going to be n times 1, n rows and 1 column. So we're going to get something back as tall as this, but as wide as this. Or in this case, we'll get something that's 1 by m, so we're going to have a row vector in that case. So we'll see the specific mechanics of that, but again, focusing on the dimensions, we have a matching dimension on the inside, and then the output is going to be those outer dimensions. M by n times n by o is going to give us m by o. Scalar, that's easy, right? It's just element-wise adding and subtracting as long as the dimensions are the same. Nice and easy, nothing you wouldn't expect. All right, we'll make a separate video to actually go through the mechanics of doing vector and matrix multiplication next.